Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at what is linear independence of vectors. And I'm going to give you a definition, and it's it's actually the definition based on what we've learned about dependence. And here's what we say: a set of vectors is independent or linearly independent when I'll write it this way, and we're just going to look at three vectors: x1 vector 1 plus x2 vector 2 plus x3 vector 3 equals 0 only when x1 is equal to x2 is equal to x3, and those all equal 0. Now remember, we said earlier that they're dependent if those x's can be different numbers. Well, independent is that one unique case when the only way, remember, dependent, there's an infinite number of ways. Independent means there's only one way. That is this way when they're all zeros. Well, if I write this linear combination in a matrix form, well, I'm going to have the matrix that has in the first column v1, the second column is v2, the third column is v3, and then I have my vector. Well, I just said that those are all zeros. 0, 0, 0 equals 0, meaning that's the only way that this can happen. Here's what this tells us. If I'm going to solve this, let's go back and let's solve this problem. So if I have v1, v2, v3 times my vector x equals 0, let's write this as the augmented matrix for a moment. v1, v2, v3, v3, and we'll put this as the 0 vector. We might have to put some zeros in it. Now what we would do is this: we would perform row operations. To solve for x. Whoops. Solve for x. Well, what do we know the solutions are? Here's what we know. We know that x1 is going to be 0. So that's going to give me a 1. Or we know, I'm going to work backwards. We know that first off, we know that x3 is 0. So if these are in R3, then I'm going to have three rows, and I know that x3 is going to be 0. That means I'm going to have a 1 there and a 0 there. If I know that x2 is 0, well, that's going to give me this form. And 0. And if I know that x3 is 0, that's going to be 1, 0, 0, 0. So what have I gotten? In other words, if I have a set of independent vectors, then through a series of row operations, I get to the solution where I have I times x equals 0. Notice this. Notice that there's no row of zeros. And let's be clear, no row of zeros when columns are independent. Okay, so when they're independent, we get I. What's so special about I? I'd like to take a minute and show you. Suppose I have this problem. Suppose I have the problem that 3 times x is, how about 6? Now, you'll probably want to quickly tell me that the answer is 2, and please do. That's fine. I can't hear you right now when you're speaking to me as a video. So what would I do? If I was to solve this, you might quickly just divide both sides by 3. But let's be more thoughtful. Let's think about what we were originally told. Originally, you said, well, this is 1/3 times 3x equals 1/3 times 6. Well, then you said, well, 1/3 is also the same as 3 to the negative 1 times 3 times x. 3 to the negative 1 times 6. Okay, well, negative 3 times 3 we usually didn't write. But if we just took a moment and wrote it, we'd write, well, that's just 1 times x equals 3 to the negative 1 times 6. But we usually don't write the 1. It's implied in our answer would have been that x is 2, but I'm going to leave it as 3 to the negative 1 times 6. Okay. In matrices, we have a similar thing that happens. We start out here. We wanted to solve the problem of a times x equals b. Okay. Well, if I was to follow this argument, then I would need this 3 inverse. This is called a multiplicative inverse. We don't use that term a lot, but that's what it's called. So the multiplicative of inverse of A is called A inverse. A to the negative 1. It's even a similar notation. Times A times x equals A inverse times B. That's the analog in matrices. But A inverse times A, well, that gives me the identity matrix times x, which is A inverse times b. And we have seen this when we've solved systems of equation, that we get an I on one side and then the A inverse b on the other side. Well, finally, though, once we've gotten to I, we know what x is, and so we don't write the I anymore, and we just write it as A inverse times b. And here's the point. Notice this. If I was to take the second to last step and write it out, I would have the identity matrix 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. You could extend this into larger ideas. And then on the right-hand side, I would have A inverse B. This would be my augmented matrix. But what's the point of this? The point of this is very simple. The point of this is that A inverse only exists when you can get an I out of your augmented matrix. The only time you can get an I out of your augmented matrix is when. It's when, right here. It's when there's no row of zeros. And that happens when the columns are independent. And that is the key thing, is that if the columns of A are independent, A inverse exists. And that's the key takeaway, is that when columns of A are independent,